All right, so it's a pleasure to have Lior here today with us, and in general to have Lior join the Circus family. So Lior comes to us from Cornell, where he did his PhD, advised by both Joe Halpern and Raphael Hess. Before coming to Cornell, Lior was an undergraduate at Tel Aviv University, where he was one of the few selected students in the honors program. And as he was a graduate student, Lior was one of the selected few of the Seeman's fellowship. So it's an extreme pleasure to have Lior here at Circus. So as hopefully you'll find, Lior's research is interdisciplinary and very, very broad. Lior will tell you more about his PhD work, but in his PhD work, Lior did built these very strong connections between very difficult topics to handle in game theory, like bounded rationality, and connecting them with concepts in cryptography and computational complexity. And at the same time, in parallel, Lior had his second life, where he did research in social networks and combinatorial optimization. So sort of these very eclectic topics that are inherently interdisciplinary. So I think that makes them for a perfect circus model. So without further ado, let's have you.
Thank you, Yaron, for the kind introduction. Thank you all for coming. Can you turn your mic on? Oh. Working? Good. So I'm going to tell you about my PhD research. My thesis was titled Only Human Game Theory with Computationally Bounded Agent, and somebody pointed out to me on Friday that I got a PhD for only being human. So I guess that's an accomplishment. Okay, so what do I mean? So game theory is traditionally defined as the study of models where rational agents cooperate or compete and have some goals. But what do we actually mean by rational here? Okay, so traditionally what we mean is that the agents are assumed to be optimal. They act optimally. They do the best they can given any possible strategy there is, and this is sometimes coined as rationality as optimization. But as we all know, agents might have a lot of limits on their ability to solve problems and how they process information and so on. And as Seeman was first to point out, this might lead to substantial simplification in the way they approach these problems. And this is usually coined as bounded rationality. Okay, so they're rational, but they have some bounded capabilities. And one interesting source of this limitation is what are the computational limitations of these agents? What problems can they solve or not solve? So my goal in this research was to study how do games, how our analysis, our understanding of what's going on in these games and decision problem changes when we model players as computationally bounded. And there's two main aspects of this goal. The first is to try and explain human behavior using these ideas. Okay, so we know humans sometimes do stuff that are considered irrational or have some biases in the way they make decisions. Perhaps we can explain this with the fact that they're just bounded. They're doing the best they can under some limitation. And this will be the main focus of this talk. The second goal is to develop appropriate models to model such agents and see how does that affect our understanding of different problems in game theory. And I will touch that in the end. I also gave a talk here last year about exactly that, so I don't want to go into too much detail about that. Okay, so why should we care? So there are two main reasons. First, if we want to build better systems, we want to be able to predict how people will use them. We want to be able to predict how people will behave. And if we can better model what people do and predict it, we hopefully can build much better system for them to use. The second reason is there is tons of system right now out there, economic systems, that are actually being played by computer programs, be it high-frequency trading or The even better example is Bitcoin, where making computational assumption is actually what makes the system work. And to be able to seriously analyze this system, we should have the appropriate model that captures the agent's capabilities. By the way, if at any point you have questions, please stop me. Okay, so there are two approaches in the literature for capturing computationally bounded agents. The first is to say that let's look at agents that can only implement strategies in some bounded set of strategies. For example, agents that can only use finite automaton as their strategies, or can only use polynomial time Turing machines. Okay? And this is the main approach I'm going to follow in this talk. Another approach is to say, let's let them do whatever they want, but let's charge them for the complexity of their strategy. So for instance, if they use a finite automaton, let's charge them for the number of states in the finite automaton. If they use a Turing machine, let's charge them for the running time, the space they use, whatever measure of complexity you can think of, let's charge them for that. Okay, and the point is that sometimes doing the optimal thing might just not be worth the effort. Maybe you can do a much simpler thing that costs you less and gets you already a lot of the optimal gain you can hope. Okay, so I'm going to start with the first part, which is this trying to model human behavior as bounded rational agents. And the goal in this part is to take behavioral models that people came up with by observing data. Okay, so they did experiments on people, and they found some behavioral models that people use. These models might not be completely rational, might have some biases, and we want to try and explain them. And the idea is to take ideas from bounded rationality and come with a theoretical model that we can prove stuff about, and as qualitatively the same kind of behavior. Okay, and what I'm going to discuss is a paper that appeared in AAAI 2012, which is a joint work with my PhD advisors, Joe Alpern and Raphael Paz. And it's called I'm Doing As Well As I Can, Modeling People as Rational Finite Automata. Okay, so why finite automata? Finite automata has been maybe the most commonly used model of bounded agents. It goes back to the 80s, where both Neyman and Rubinstein, in two separate work, used it to explain cooperation in finitely repeated prisoner's dilemma, where we know the only Nash equilibrium is for both players to defect. If you don't know exactly what it is, it's not that important. But this is the first example for using finite automata to explain why people don't do what the theory predicts them to do. So the more related to our work is this work by Andrea Wilson from 2002, where she, I don't know why this is, let me check what's going on. Okay, where she studied the following decision problem. So nature is in one of two states, and the agent needs to decide which state it is. It's either red or green, and it never changes. The agent gets signals about the state, one of k signals, and the ith signal provides stronger evidence for the state being green, and the k signal provides higher evidence that it's red. And at some point, with some very small probability, the game ends. Okay? At each round, you get one signal, and with some probability, this is the last signal, where you then have to make a decision. And if you're right, you get a payoff of 1. If you're wrong, you get 0. Any questions? Yeah.
The agents only see the signal? Or
Yeah.
do they see what other agents?
No, it's a decision problem. There is only one agent. You get signals. Think of that as deciding if to buy a home or not. You collect a lot of information about it. You get signals from various places. You want to decide if you're going to invest a lot of money in buying this home or not. So eventually, at some point, the broker tells you, you have to give me an answer now, and that's the end of the game. And hopefully, you're able to make the right decision. Okay?
The presentation is giving itself.
Yeah, I'm not.
It might be that it's using recording time in the presentation.
I have no idea how to stop this. anybody know how to stop this? Okay, let's open stop. Okay, so any question about it? Yeah? You want?
So the game ends like very quickly, essentially.
No, so think of this as very small probability.
But it's constant.
It's constant, yeah. It doesn't depend on any other parameter of the model. There is some very small number.
So in particular, I'm not getting enough signals to get concentration bands?
You are. So hopefully the game is long enough for you to be able to. So I will explain why it's not that simple in the next slide. Okay? Yeah.
And that's also my question. Because the signal is drawn from some distribution.
So you know how the signals are correlated with the state of nature. Okay, sorry. So the signals are somewhat correlated with the state of nature. If the state is green, you are more likely to get the signal K. If the state is red, you are more likely to get the signal 1.
And the agent also knows this.
He knows the distribution. So if it was unbounded, as Yaron pointed out, this was very simple. Just collect all the information and do some Bayesian inference from that and make the best decision given that. So if an agent was unbounded, very simple what you should do here. Not a very complicated model. Yeah.
I guess maybe this won't matter, but are red and green equally likely a priori?
Yeah. Okay? So the point is that the agent is going to be bounded. We're going to think about him as a finite automaton, and what Wilson does is finding, given any number of states, any number of n states, she describes exactly the optimal thing an agent should do with these n states. Okay, so say I tell you have to use a finite automata with 10 states. Wilson tells you what's the optimal thing you should do with 10 states. Okay? And let me describe you. And she does that given that the probability the game ends is small enough and that there is some information in the signals, right? If all the signals are like if there's no correlation between the signals and the state of nature, there's nothing you can do. And let me tell you what the optimal thing to do. It's pretty simple, surprisingly. So you put the states linearly, okay? You number them 1 from n, and you never jump over states. All your transition is from I to I plus 1. There is some threshold state j that you can compute, in which if you are before that state, when the game ends, you say red. If you're above that state and the game ends, you say green. Okay? If the signal is 1, you move left. You move 1 state left from where you are now, with some positive probability. If the signal is k, you move right 1 step with some positive probability. If the signal is any other thing, you just don't move. You ignore it.
And how do you initialize the?
There is also some initial state you start at, but it really doesn't matter because the game is long enough. It doesn't matter where you start, as long as you're not in one of the extreme cases. Okay, if you are in the last state, state n, you still move if you see 1, but the probability you move is very, very small. It goes to 0 as it depends on the probability the game ends, and it goes to 0 as that probability goes to 0. So it's a very small probability you ever leave the edge state. It's also symmetrically true for the other state. Okay? What it means is that if you get to one of these extreme states, you essentially made up your mind. It's very hard to convince you now that anything is different, okay? No matter how many signals you see for the other direction, the probability you'll ever leave that state is very small. Okay, and that's the optimal thing to do, given some limit conditions, okay, on the probability the game ends, and that there is some information in the game. Yeah?
So the deviation from the rational model is great when I'm at that state and I'm willing to leave. So how should I compare this with
So an unbounded agent will always look at all the signals so far and will do a Bayesian inference from that, right? Here you're only keeping a very small amount of memory. That's the first thing. And the second strange thing is that these extreme cases you don't live. You almost never live them, okay? Which is what she uses to say that this explains why we see stuff like first impression bias, okay? Think that you started somewhere and you got a lot of good signals, a lot of green signals. You got here, and now no matter what you see, it's very unlikely that you'll decide it's green. Okay, so you are very, if the first few signals told you that it's red, you're very biased towards that. The second decision bias she explained with that is something called belief polarization, that says that take two people that had slightly different priors about the world and give them the exact same set of signals, they will end up with completely polarized beliefs. Okay, and this is used in jury, for instance, where two juries that see the exact same trial, the exact same evidence, come up with completely different verdicts. Okay, and this, I think that the two of them started in slightly different places on this automata. One got stuck at the green, one didn't get stuck, and suddenly all the evidence are towards red. He won't be convinced of that. Yeah.
How many? So there's n states. Is n is just a fixed number?
So for any number n, this is the optimal thing to do.
So
okay?
n doesn't relate to any parameter of.
So the probabilities will depend slightly on n, but with any n, this is something like this is the optimal thing to do. Okay, the parameter. I haven't told you how to compute the probabilities and stuff like that. Not important. Okay. Good. So here is an example that by viewing people as resource bounded, we can actually explain known biases in how people make decisions. Okay, so these are observed phenomena in people decision making that are irrational, but there is an explanation. They're actually rational if we think of people as finite automata. Okay. Yes.
So can you explain, why is it optimal to ignore all the k-2 signals?
So I can give you a very intuitive, so this paper took 13 years to get published, okay? It's 2002, it's actually in Econometrica 2014. So I can give you an intuitive idea. If the game is long enough, right, it doesn't matter. You will eventually see the strong signals, and you should only look at that. So that's in a very intuitive level why it's okay to ignore the signals. Okay? Did that satisfy you? I can't give you the technical reason, and I won't even try.
It took like 12 years to review the technical details.
And there were a few revisions and.
Didn't anybody that was worth it?
No, worth it. I think it was like people understood it from the beginning, but it wasn't well written. Blah blah blah. Like I don't know. I don't know her. I don't want to talk in her name. Interestingly, it was also studied in the 70s by Cover and Ellman. A very similar thing in a completely different scenario, but they got very similar results. So she had to also explain what she did differently. The story I heard is that she gave her PhD defense or something like that, and somebody raised his hand and told her, I think it was done in the 70s or something like that. But this can be a folk story. I don't know if it's true. Okay. Okay, so I describe you this model, but this model assumes that nature is static. Nature never changes, and you eventually need to tell me what its nature, what its state is. But in many important decisions, nature changes, right? So think of, instead of buying a house, you want to invest in the stock market. Stock market fluctuates. Sometimes it's good to invest, sometimes it's bad. And think about you getting signals about the stock market at any point. You need to decide if you're going to put more money, take your money out, or just keep your current option, okay? And we want to come up with a model that can help us capture what happens when in these dynamic situations. This work is partly motivated by this model by Earth and Roth, where they wanted to find out what people do in this dynamic situation. And they gave people to play a game where they had two options. They can either play risky, in which case their payoff depends on some state of a game or some state of nature, and they can play safe, in which case they get a guaranteed constant payoff. And the state of the game can change dynamically. And they ran this experiment with many parameters on many different subjects and in different settings of how the payoff behaves and stuff like that. They collected a lot of data and then they put it online and asked people to come up with models that best predicted this data. Okay, come up with behavioral model that best fit the observed data. And the model that won is a slight variation of something they called ISO model, and ISO is for inertia, sampling, and weighting. And basically, this model has three behaviors. First, with some constant small probability, you explore. You do exactly the opposite of what you did last time. If you didn't decide to do that, you keep on doing what you did, unless the last signal you got completely surprised you. It was something you completely didn't predict. In which case you do exploitation, you look at the last few samples you have, and you make your best decision given that, which they call exploitation. Okay, and this with certain parameters was the best thing that fit all the observation they got from running these experiments. This sounds very plausible, right? This is probably what most of us will do in that scenario. Yeah.
How do you fit the model?
So I'm not exactly sure how they fit the model, but they ran it instead of the players, I guess, and saw what's best.
And saw what predicts
Yeah, exactly.
good behavior best.
Yeah. Okay. It's not what I did, so
No,
I'm
sure.
okay. So we can all agree that the ISO makes sense, and apparently it describes how people behave, but it doesn't say why. Okay, so we're interested in why. Why do people behave that way? And more precisely, is this behavior rational? Okay, it's not what the unbounded Bayesian updater will tell you to do. Okay, if you know how the game behaves, you can collect all the samples. You don't need to do inertia. You don't need to do anything. Just always look what the best probability is and make your decision like that. Okay, so we want to try and say that this actually makes sense. Okay, and what we'll show is that this can be viewed as the result of a resource-bounded agent doing the best it can. Okay, and we'll do that by giving a very simple finite automata and showing both theoretically and by simulation that this does very well in practice. Good. So let's first formalize what is the decision problem now we're facing. So again, nature can be either good or bad. And now there will be some probability pi of nature switching state, and think of pi as something small. Okay, if nature changes very quickly, then there's no learning, right? There's nothing. You're not really learning its state if it changes frequently. And now the agent has two possible actions. He can play safe or risky. If he plays safe, he just gets 0. If he plays risky, then he gets some positive payoff when nature is good and some negative payoff when nature is bad. Good. The agent won't learn this payoff. He instead gets one of k signals that are correlated with the state of nature. You can also think of that as getting, instead of getting this xg or xb, getting some distribution of payoffs. Okay, if he's right, he gets the payoff distributed with an expectation of xg, but there is some overlap between the two states. But we will just think of this as getting one of k signals that are correlated with the state of nature. But he will only get the signal if he plays the risky action. If he plays safe, he doesn't get action. And you can also think of that as an extreme case where he just gets a worse signal. Okay? Maybe he gets some information, but a much worse signal. And think of, I don't know, at least me, when I invest in the stock market, if I'm actually in it, I try to read the paper, see what's going on. This was before I was a grad student, when I actually had money to spend on the stock market. But if I'm not there, then maybe I get there, like, you know, if there's a big headline, I learned something that the market went really up or really down, but this is not really an informative signal. I don't really follow it. So think of that way. Okay, so I only get a signal if I actually play. Okay, so what is the agent I'm going to assume? So I'm going to assume a bounded agent, and it's going to be a finite automaton, and I'm going to focus on a very specific family of automatons. It will have n plus 1 states that I'm going to put linearly as 0 and 1, and you're going to split the case signals into 3 groups: the positive signals, the negative signals, and the indifferent signals. And this is how it's going to behave. In state 0, it's going to play S. In all other states, it's going to play risky. Okay? And when he's in state 0, with some small probability px, he's going to go to play 1. He's going to move to state 1 and play risky. Okay? When he's in state 1, he gets signals. So now if he got a signal in pause, he will move 1 state above with some positive probability. If you get a signal in neg, you will go to the left. And this transition probability won't depend on the state, not like in Wilson's model. Okay, this will be the same throughout all the states. And if you get a signal in I, it will not do anything. So 2 points. First, this is very resembles of the Wilson's automata, right? It has very similar, some similar characteristic. And B, this is something we can imagine people implementing in their head, even if they're doing it unconsciously. This is a very simple thing to believe that something like that is being done. We get some signals, we say, oh, okay, nature is better. And now we record in our head that nature is in a better state than we thought before, and so on. Okay, and this strategy has the same qualitatively behavior as the ISO model I described to you before, right? So it has this exploration thing. When it's in state 0, it sometimes just do the opposite thing. It plays 1. If it's in a state bigger than I, then if the signal was meaningful enough, meaning it was in pause or neg, not the indifferent signals, then I'm surprised, and I'm gonna, unless I got that, I just keep on doing what I did. If I got such a signal, I exploit the information I have, okay? So think of the state of the automaton as keeping some information of the observation I had so far. Okay, if I'm in state 4, it means I got 4 good signals that I decided to remember so far. So I exploit the last few samples I decided to remember. So it has the same kind of qualitatively behavior as the ISO model. So if we can prove that this is a good strategy, we can use it to explain that why people use this behavioral model. So here is our theoretical result. We show that under some limiting condition, if nature doesn't change too quickly and we have enough states, that this is actually optimal. It's optimal not just as a finite automaton, it actually achieves the optimal possible thing that an agent can hope to get. Okay, yeah?
So what's the agent's objective here? So is it to maximize some of it?
So the game never ends, and he wants to maximize his expected average payoff. No discounting, no nothing. He wants to get, think of the limit of mean, the limit of the mean. Yeah.
But he is a computational bounded agent here. So
Right.
So if he wants to compute the limit, he has to sort of.
He doesn't compute it. That is objective. He wants a strategy that guarantees that he will get, if the game goes forever, he will get the best average payoff. He doesn't have to compute it to optimize. Right? If you run it forever, you can also compute it. But that is objective. Good question. I forgot to mention. Okay, so that's what we show. Okay, if nature doesn't change too fast, right? If nature changes fast, you're hopeless. There's nothing you can do. You get, like, there's no information. You can't really, even an unbounded agent can't do much. And if you have enough states, then you get arbitrarily close to the actual optimal. Okay? And not the optimal with the finite automaton, any optimal. Good. So the way to prove that is to argue some stuff about the Markov chain that this automata actually presents. The automata together with the nature behavior, you can define a Markov chain on it, and then try and prove some bounds on the limiting probabilities. And we do that and show that this bound goes close to xg over 2. So if you think about it, this is the theoretical optimal, any agent, no matter what it does, even if he knew exactly what nature state is at any point, this is the best he can hope to get. Because nature is symmetric, it is going to be f of the time good and f of the time bad over the, if you take the limit. And when it's good, you're going to play, you're going to play risky and get XG, and when it's bad, you want to play safe and get 0. So this is the best any strategy, even an Oracle strategy that knew exactly what nature is, can get. And we show that this approaches XG over 2. Good. So we show that this makes some sense, right? If we get enough signals and if we have enough states, then this is a good strategy. It's optimal. But we're not, but we want to know what happens only if you have a few states, right? We want a finite automaton with 10 states, like Wilson did. Okay, so we weren't able to theoretically prove that this is the optimal thing to do with 10 states, so instead we resorted into simulation, and we wanted to show that it does pretty well. Okay? So I'm going to show you the simulation result where I had 4 signals, and this is the probability when nature is good, and the exact opposite when nature is bad. And the payoffs are 1 and -1. Okay, so the best optimal is F. That's what I want to achieve. And nature doesn't change too often, once every 1,000 steps in expectation. Good. So the red line is the optimal, right? I told you you can't get more than F. This is the number of states that the automaton had. Yes.
How many rounds is this?
I don't remember.
So
like
large number.
Large number, yeah, like 1 million, say. Much larger than 1,000. So it changes back and forth a lot of times. And this is the average payoff. Okay, the black line is the average payoff of the simulation, and the dotted line is what I got from the theoretical bound I had from the previous theorem. Okay, so the previous theorem gave me some lower bound on what the payoff is that went to F as the nature probability went to 0, and I had more and more states. But this is with a constant number of states. Okay, so first you can see that already with about 7 states, I get 0.43, which is almost optimal. It's like 15% less than the theoretical optimal. I'm not sure what the optimal you can do with an automaton or what the optimal a Bayesian even does here, an unbounded agent does here. Okay? So it does pretty well, right? It doesn't lose as much. Yes?
Why shouldn't I be bothered by the fact that making my agents
I'll talk
more
about
powerful? Okay, thank you.
I'm about to make too.
it. Yeah, I'll talk about it. Okay, second, in this plot, I for each number of states, I've searched the other parameters to be optimal. Okay, I did like a grid search over all the rest of the parameters of the agent, and this is the optimal one, but it's not very sensitive to that. So it's pretty robust. You don't really need to optimize that exactly for each type of parameters. If you change the signals a bit, it also doesn't change by much. The plot looks very similar, and the parameters don't. If you change the parameters by a lot, of course the agent's parameters also change, but as long as the changes are not very extreme, the same kind of strategy performs pretty well. Which is important because as I think I think of it as we have some decision algorithm in our mind, and we use it where it's appropriate, and I don't want to fine-tuning for every specific problem. So if you want to say this is maybe what people do, it should be pretty robust. Good. And now back to Margot's question, why is this dropping? So no matter how many states I had, I kept the same exact strategy. I didn't try to change the strategy. Okay, so I kept that very simple strategy. So one thing I can do even if I have more states is to cut it off at 7, right? But what actually happens? What actually happens is that the agent becomes stubborn. Okay, you've been in a good state for a while. You've seen a lot of states. Now you're in state 30 in the automaton. And now nature switched. It takes a very long time to convince you of that because you're so stubborn. You think you're in state 30. You need 30 good signals to convince you that nature has changed before you go to play before you decide to play safe again. So that's why actually having more states, if you insist on using this simple strategy, having more states hurts you. And this suggests why we have what's called a recency effect, which is exactly the opposite from first impressions. Okay, recency effect says that people tend to look at the last few signals and make decisions according to that. So even if you got 1,000 bad signals and then suddenly you got 10 good signals, people tend to say, okay, so I got 10 signals, it means nature is good. Although if you do the Bayesian rule, maybe it's not enough. But it says, actually 7 is good, okay, under this parameter. I actually like the fact that it got to 7 because people used to say that humans are able to remember between 5 and 7 objects. Okay, so this is good. This is about 7. Makes sense. Yes.
So if the distribution of good and bad, like if the prior probability of being in good or bad was not 50-50,
Yeah.
would you still see this like, still see the fact that 7 is really good as opposed to a larger number?
So I don't think I've checked that. I'd never played with asymmetric. Right, this is symmetric by, like, nature only changes the probability pi no matter where he is. I don't remember that I played a lot with having different changes from bad to good and good from bad, but we can take this offline. I can check. Yes?
What about changes in likelihood of more good and more bad? There's a very robust literature that says that we remember bad, that bad is stronger than good. That I'm much more likely to react on a negative signal than I am to a positive signal.
Okay, so
I'll have more inertia going this way and have less inertia going back.
good. So in some sense, I haven't thought about it until now, but in some sense you can say that this is also happening here because I have only 5 states that I keep. The most I remember is that I saw 5 good states. Now if I get 5 bad signals, okay, so if I get 5 bad signals, I'm going to say, oh, nature is terrible. So I'm much more inclined to react to bad signals. Now I play safe for a while, I don't even listen to the signals. So even if now I should have gotten good signals, I won't react to them. So this has the same kind of behavior actually. And yeah. Okay. So did that answer your question?
That's interesting. I wonder if instead of reacting to the signal, you could react to some decaying probability of the last n signals. So some moving
So
average.
it
some
might,
clever.
but I want to keep it very simple. I don't want the agent to do anything smart.
Okay.
I want him to be very stupid because I believe that's what we did. Look, so one more point to stress out. All of these experiments are done on psychology students in some lab for $1. They're not really putting their entire mental effort in this serious problem of trying to figure out if nature is good or bad. I believe that if it's life or death decision or buying a house, you're gonna, as a human being, even put a lot more effort.
I'm not convinced.
Maybe it's worth experimenting with that, but that's very much harder to experiment, right? So I'm trying to think of very simple thing to do, and I'm gonna argue something about maybe there's something better, but that is more complicated in a second, okay?
Maybe you're renting an apartment.
Yeah, exactly. Yeah, it took me a month to find an apartment here, so I guess I was putting too much effort into that.
So there may be a different interpretation for why having more states decreases performance. So in general, there are examples in game theory where where increasing the strategy space actually hurts players.
Yes.
So I mean, it's just a different, slightly different.
So it's true. Like, of course, with more states, you can never hurt yourself, right? One thing to do is just not use them. Like, here is a strategy with 10 states, ignore the last 3 states and behave as if you have 7, right? And I haven't tried to, okay, it can never hurt you and it should improve you, right? But as I said, I kept a very simple strategy with the 7 states, so kind of good.
I don't know, I guess that 7 is bothering me and that it feels like it's gotta be a function of some of the print, like.
Yeah, of course.
You know.
Yeah, it won't be 7 for every, I'm like, yeah.
Yeah.
I like this scenario because 7 is a good number, but yeah, of course, if you change the parameters, if there's a lot more signals, it won't be 7. I'm just overstressing the 7. Any other questions?
Well, the real question then is, what is the 7 a function of, right? What
So it's a
is
function
there-
of all the number of signals, their probability.
Well, and is there, I mean, can
And
you express
if
it?
nature changes a lot less frequently, it should be less than 7.
Right, so it's-
More than 7,
So
sorry.
is there a closed form expression
No,
of what
not
number
that we
is?
could find.
Okay.
Okay, not that we could prove.
So people with different personality types. will
What?
behave- People with different personality types will behave the same way?
So this, I don't know, but this just says that if they behave this way, it makes sense. I don't know, maybe.
So
You know,
in
some
that
people
case-
take every small task they get very seriously. They'll probably put some more effort than running this very simple algorithm on it. I don't like. But as I told you, the experiments were very robust. Like the experiments other people ran on people, they got 100 of people running the same kind of game, and then they came up with a model that best fit that data, and it was pretty robust. So probably you get different behaviors by different people, but on average, that's what people do. Okay, any other questions? What's the time?
It is 12:19.
Okay, so to summarize this part, we described a very natural and simple strategy that does pretty well. Okay, both in theory, it makes sense, and in simulation, we show that it gets very close to optimal. And it might not be the optimal strategy, not even with 7 states. Okay? But it seems not far from what people do in reality. And second, if you think about I said there's 2 approaches in the literature for modeling bounded agent. I use the one. It has to use a 7-state automaton, okay? With that family of strategies. But think that I'm now going to charge you for the complexity. So maybe there's something much more complex that does better. But if it doesn't have too much to gain anymore, right? There was like 15% there from the theoretical best optimal thing to do. So if it's a lot more complex and you charge me for doing that, my mental capacity for doing something much more complex is expensive, maybe it's just not worth it. So it might not be the optimal, but it might not be worth actually running the optimal thing here. Good. So going back to my motivation, I looked at this ISO model, which came from the observed data. This is a behavioral model of people, and I used bounded rationality, and more specifically a finite automaton model, to show that they are qualitatively similar, and I could prove something about this finite automaton. I could analyze it. Good. So interesting question, is this optimal? How much better the optimal does? Is it a lot more complex? These are questions you people also that you raised yourself. It's interesting. I'm not sure if it will change what our conclusions. Another question, this was a completely decision theory. There was one agent and he behaved, he interacted with nature. What happens if there's a lot of agents? They do this in parallel. Maybe some are a little bit stronger than the others. Can we use that to explain a lot more complicated phenomena like bubbles in the stock market? Maybe because people do this simple thing, it's very easy to manipulate them into creating bubbles and stuff like that. Once you have weak and strong agents interacting with such strategy, what happens? And in general, can we look at more complex human behaviors and explain them with similar approach? Okay, any questions about this part before I move on? Okay, so now I just want to give you a flavor about the other part of the work, because I already gave a talk at the CRCS seminar, I think a year ago. But I think most of you weren't there, so I want to give you a flavor of the kind of results we proved. And this is based on a paper called The Truth Behind the Myth of the Folk Theorem. And I hope by the end of these 5 minutes you will understand where this title is coming from. And this was in ITCS and Wine 14. And this is also with my PhD advisor. Okay, so Nash equilibrium is the most basic solution concept in game theory. Okay, it tries to predict what people do in dynamic games where they compete with each other and have conflicting goals. And finding a Nash equilibrium, or the complexity of finding a Nash equilibrium, is one of the main questions in the intersection of game theory and computer science. And there's a celebrated sequence of results showing that this problem is computationally hard, or more precisely PPED hard, which is a complexity class considered intractable. Okay, and this is even if you have only 2 players, and even if you're allowing approximation, so epsilon Nash equilibrium it doesn't matter. It's still a very hard computational problem. Good. So what does it mean? Why do we care about that? So there's a famous quote, I think it's people say Kamal Jain gave this quote, if your laptop can find it, neither can the market. Okay, so if your laptop can find a Nash equilibrium, you shouldn't believe the market finds a Nash equilibrium, because the market can't be smarter than, it can't solve intractable problems. So perhaps Nash equilibrium is not a good solution concept, right? If we don't believe the market computes it, it's not predictive. But this kind of statements implicitly assume the players are bounded. It assumes the players can compute PPEDR problems, right? Otherwise, we shouldn't care about that. So here, the question is, how should we model that? Right, if we allow the players to be unbounded Turing machine, there's a trivial solution. They first compute the Nash equilibrium and play by it. That's their strategy. It's not very complicated. The question is, what changes if we explicitly model them as computationally bounded? Okay. So I'm going to use repeated game as my example for what happens. And repeated games are just the same. You take the same simple game and play it over and over again. And now the player's objective is to maximize their discounted average payoff. There is some discount factor, and they want to maximize their average payoff. They don't care about every single game. Okay? And in these games, there is a famous result called the Folk theorem that states that almost everything is in equilibria. And the idea there is that I can force everybody to do whatever I want, because if they diverge from that, I can punish them then for a very long time. So I can tell everybody to play a certain strategy, and once somebody doesn't do it, I can then punish him in the rest of the game. So the best thing for him will be just to follow the strategy. So almost everything is a Nash equilibrium. So if we have such a large set of equilibria, maybe just finding one is easy, right? I just want to compute one Nash equilibrium in this large set. That should be easy. And indeed, in two-player games, there is a paper showing you can use this idea to find a Nash equilibrium. So there is some hope, right? With two players in a single-shot game that I described before, it's PPEDR. You can compute it. If it's repeated, you can. Okay, so this gave some hope that this problem is actually easier. But unfortunately, there is a beautiful paper by Borg et al. Called The Myth of the Folk Theorem, saying if you have 3 or more players, it's still PPEDR. Okay? So no gain from going to the repeated game model. Yes?
So does this paper, do they consider perfect monitoring?
Yes. You get to see everything. I'm going to consider that as well. Okay. So here's the catch. What Borg et al. Do is that they state the problem as finding polynomial time strategies that are Nash equilibrium, but the deviations they allow are arbitrarily. So a player that wants to deviate can use any strategy he wants, including unbounded Turing machine. He can do whatever he wants. And I want to say this is not okay. We should model also the deviation as only being strategies that can be implemented by polynomial time Turing machine. Okay, so I'm going to make all the players and whatever they can do be polynomial time Turing machine implementable. And additionally, I'm going to assume some cryptographic hardness assumption that that polynomial time Turing machine can solve some cryptographic problem. Okay? And this actually changes the landscape. What we show is that if you make this assumption, then we can actually compute the Nash equilibrium. And the main idea is that we use folk theorem strategy with a slight twist. Before the punishing starts, the players that want to punish use cryptography within the game. They don't have outside channels. They use the game to communicate in a way that is secret from the player they want to punish, and then they get correlation, and we're back to the two-player case. When they want to punish, they all act as one player against the player they want to punish. And as we said, with two players, we know how to find Nash equilibrium. Okay, so this is the twist, and it overcomes the hardness shown by Borg et al. Because in Borg et al., if I use cryptography, the other player can defect to a strategy that breaks the crypto, right? He can do whatever he wants. He can be unbounded. He can just defect to that. So that's how we overcome this hardness. So to conclude, in real life, agents are computationally bounded, and we should model that explicitly in our model. Like, this is exactly why we care about equilibrium computation, or one of the reasons we care about that. So we should model this. And it has surprising consequences, okay? Problems that we considered as computationally hard suddenly became computationally easy. And in a follow-up work, we also showed this is true for computational subgame perfect equilibrium, which is relevant in repeated game. If you don't know what it is, it doesn't really matter. Okay, so future direction in this part is what other problems in AGT are affected by this kind of assumptions? Can we say something interesting about other problems? And more generally, how should we model games played by computationally bounded players? Can we get a general enough model to capture modern systems like Bitcoin, or analyze any economic system where computer programs are actually being used? Any questions about that? Yes.
So about the result you talked about a couple of minutes ago. So if the parties implement the cryptographic protocol, or if you call it within a single player, I wouldn't claim this is the behavior we see in general in humans.
No, I agree.
Here's the question.
So
Could we design this maybe, so we could think about secure multiplayer computation against a much weaker opponent, like maybe an automaton.
yes.
Instead of an opponent on Turing machine. And then is there a chance of constructing these protocols in a way that would resemble more the way humans interact?
So yes, I completely agree. I think this is just, using crypto and polynomial Turing machine are tools we use because we know how to analyze them. I completely agree that that's not what we do in practice, but I do believe we try to communicate and interact in ways that are hidden from another player, but we're using much less sophisticated things than full-fledged crypto. And I think it's very important to try and come up with models that are against much weaker opponents. So I'm not familiar with too many protocols that are designed that way, or any, but we have some follow-up work on trying to generalize this into a model where players are bounded and then trying to connect information in games with indistinguishability. And I think there, if you can define indistinguishability for finite automatons or another restricted computational model, then our result should directly go there. And yeah, did that make sense?
Yeah, I think so.
We can talk about it offline as well. Yes.
So have you thought at all about comparing sort of the computationally bounded viewpoint with some of the other behavioral game theoretic models like quantal response and other things like that?
So I thought a little bit. I don't have any result, but my guess is that you can come up with the ways with ways to explain quantum. I thought about it a little bit, but.
And then I guess just one observation I have is that one thing that's nice about these other models that they're sort of geared towards being able to fit them on data.
Yeah.
And do you have any sense of how I would, like, if I had a favorite computationally bounded model, how would I fit it to data?
I haven't tried, so no. Yes.
So I have it's a similar problem. Think of a game where you get inputs and then at some point have to make a decision. So the example would be you're a bird and you have to decide whether or not to flee. And you're getting safe versus danger decisions, and at some point you have to flee. Now think about that game, it's very different in the payoffs. If you flee, you lose some amount of feeding time or whatever. If you don't flee, there's a probability you'll get eaten and die forever. And there's a lot of interesting work in the optimal strategy for very bounded way of dealing with it. There's a paper by Ness called the smoke detector principle, which basically says alarm all the time. You see that behavior in birds. The thing about that optimal strategy is it's optimal not for the individual but for the population.
Mm-hmm.
And I'm wondering if there are If there's anything interesting in looking at it that way.
So I'm not familiar with that work, but there is a paper by McNamara and some
Yes.
co-author in biology that actually studied the exact same model. We found out this very, very recently, and they come up with some strategy that's supposed to show what birds actually do. It's a feeding. You need to choose between a risky food source and a safe food source. And we actually showed that our strategy does much better than theirs. And
So you're gonna make a better bird, you're saying?
I think our strategy also explains the behavior they try to explain. And I don't know, there's something weird. We can talk about if you're familiar with that
I'd love
word.
to trade those papers, I wanna read the one you talked about.
Okay, so I can send it
Yeah.
to you. And we're thinking about writing some response. We tried to contact them and they haven't replied. But
That's probably their optimal strategy.
yes. So they actually studied the exact same type of strategy, but they come up with a different model that I don't completely understand why it's good. But never mind, we can take it. Any other questions? Yes.
I just have a clarification question for the last part that you talked about. So will you say that you restricted the deviation only to strategies that's tractable?
Yes.
essentially? So is that the calculating the deviation to be tractable, or is
No.
restricting to the strategy space?
The strategy space is only tractable strategies. Computing the deviation can be, I don't care about it.
You don't care about, so basically it's a restricted strategy space
Yes.
and defining the equilibrium based on
On that, exactly. So the deviations have to be in a class of polynomial time computable. Like this should be a Turing machine that is polynomial time implements that. It actually becomes tricky to define it. I gave a very informal description, but in the paper we formally define what we mean. It gets tricky.
So
That's
the notion of the equilibrium hasn't changed, except that the strategy space has changed.
yes, you can look at it as both. Yeah, like usually you say any strategy you can do better than any strategy. So we do. It's not any strategy. It's any strategy in a set of restricted set of strategies.
Okay,
Okay, thank
thank
you.
you.